Welcome back to The Explainer. So glad you're here. Today, we're unpacking the mechanics of climate change, and we're going to do it by looking at this really fascinating concept, the invisible blanket that surrounds our planet. We'll be sticking strictly to the data to break down exactly how this planetary mechanism works, layer by layer. Let's get right into it. Here's our roadmap for today. We're going to start with global warming and its impacts, then we'll explain the greenhouse effect, meet the actual greenhouse gases, and look at climate forcings and aerosols. After that, we'll talk about measuring global warming potential, and finally, we'll zoom in on some micro impacts on the ground. All right, Section 1, Global Warming and Impacts. Simply put, this is an average increase in the temperature of the atmosphere near the Earth's surface, which today is primarily driven by human emissions. So just what happens when that average temperature shifts? Well, it sets off a pretty rapid domino effect. We're not just talking about warmer summers here. We're looking at rising sea levels, totally disrupted rainfall patterns, and a huge spike in extreme events like floods and hurricanes. We've got melting ice caps and glaciers, which obviously threatens animal populations with massive habitat loss. But it hits us directly too, helping spread diseases like malaria. And if you look at the oceans, this warming is causing widespread bleaching of coral reefs and a serious loss of vital plankton. It's truly a comprehensive global shift. Moving on to Section 2. The greenhouse effect explained. To understand these massive impacts, we really have to demystify the actual mechanism causing them. Now, what's really fascinating here is that the greenhouse effect is absolutely not an inherently bad thing. It's actually a naturally occurring, incredibly vital phenomenon. Think about this. Without this atmospheric blanket, Earth's average surface temperature would be a freezing minus 19 degrees Celsius. We'd literally be a frozen, lifeless rock. But with the natural greenhouse effect, our average temperature sits at a very comfortable 15 degrees Celsius. It literally maintains life as we know it. The issue isn't the blanket itself, it's just how thick that blanket is getting. So let's look at exactly how this blanket works. Step 1, the sun. It's incredibly hot, so it blasts energy toward us in these high-energy short wavelengths that just punch right through our atmosphere. Step 2, about 30% of that energy bounces right back into space, off clouds in the Earth's surface, and the rest is absorbed. But here is the crucial aha moment in Step 3. The Earth is much cooler than the sun, right? So when it re-emits that energy back up, it does so in the form of long-wavelength infrared radiation. That's the key rule here, short wave in, long wave out. Our atmospheric blanket ends up trapping a lot of that outgoing long-wave radiation, keeping the heat inside. Human activities, like burning fossil fuels and deforestation, are basically just packing more and more insulation into that blanket. All right, Section 3, meet the greenhouse gases. Let's look at the specific threads that make up this invisible blanket. Let's give each of our main culprits a quick profile. Water vapor is actually the biggest overall contributor, but it cycles through the atmosphere super fast as rain or snow. Now, humans don't emit it directly enough to change its concentration, but as other gases heat the Earth, evaporation goes up, which means more water vapor gets trapped. Next is carbon dioxide, or CO2, which is the primary gas emitted by human activities like burning fossil fuels. Then we've got methane. This naturally comes from wetlands and termites, but a massive amount comes from human agriculture. Yeah, we're talking about cow burps here, and natural gas leaks. Nitrous oxide naturally occurs from soil bacteria, but things like synthetic fertilizers and transportation fuels are really spiking its levels. And finally, look at those fluorinated gases at the bottom. Notice the natural source? There isn't one. These are completely synthetic, coming from aluminum and semiconductor manufacturing. They are highly potent, stick around for a very long time, and can only be destroyed by UV radiation way up in the far upper atmosphere. That brings us to Section 4, Climate Forcings and Aerosols. If greenhouse gases are the blanket, forcings are the wild cards of the climate system. A climate forcing is basically any factor that alters the climate. And surprisingly, not everything we put into the air warms the Earth. You've got positive forcings, like our excess greenhouse gases, which definitely warm the planet, but you also have negative forcings. Things like the dust from massive volcanic eruptions or certain atmospheric aerosols can actually cool the Earth down by blocking incoming sunlight. A really fascinating example to look at here is black carbon. Now, it's not actually a gas, it's a solid particle, commonly known as soot, which comes from incomplete combustion like diesel exhaust or burning biomass. It warms the air directly by absorbing heat. But even more critically, when this soot lands on snowpacks or mountain glaciers like the Hindu Kush Himalayan glaciers, it physically darkens the ice. This reduces the ice's albedo, or its ability to reflect sunlight, which seriously accelerates the melting process. But there is some good news here.
black carbon only stays in the atmosphere for days or weeks. So if we actually cut emissions, its warming effects would disappear within months. Now contrast that with brown carbon. This is a much newer focus in atmospheric research. While black carbon is soot from impure combustion, brown carbon refers to light-absorbing organic matter, think terry materials or bioaerosols. Our source notes that the major culprits for this one include biomass burning and smoke from agricultural fires. Moving right along, Section 5, Measuring Global Warming Potential. We know what these elements are now, but how do scientists actually measure their varying threats? It's a great question. I mean, if water vapor cycles fast, methane comes from cows, and fluorinated gases come from making semiconductors, how on earth do we compare apples to oranges to figure out the real effect of each gas? Well, the data shows us it really comes down to three main factors. Number one, concentration. Just how much of this gas is actually up there in the air. Number two, lifespan. Once it's up there, how long does it remain well mixed in the atmosphere before it eventually breaks down? And number three, heat absorption. Pound for pound, how effective is this specific gas at trapping that infrared radiation and thickening the Earth's blanket? To understand that first factor, concentration, scientists use measurements like parts per million. But what does that actually look like in the real world? Our source provides this fantastic analogy. 1 part per million is exactly like taking one single drop of water and diluting it into 13 gallons of liquid, which is roughly the size of a compact car's fuel tank. It sounds absolutely microscopic, right? But on a planetary scale, every single drop matters immensely. To wrap all three of those factors together, scientists use a metric called GWP, or global warming potential. This describes the total energy a gas absorbs over a specific period, usually 100 years, using carbon dioxide as the baseline. So if a gas has a higher GWP, it means it absorbs significantly more energy per pound than CO2 does, making it a far more intense contributor to warming the Earth.
And finally, Section 6, Micro Impacts on the Ground.
We've spent a lot of time up in the upper atmosphere, so let's bring it back down to Earth for a minute. These massive global changes create highly specific, localized disruptions. Take the Shola Forests, for instance. It's a temperate, evergreen ecosystem found at high altitudes in southern India. It's totally confined to sheltered valleys and depressions, requiring really well-drained soils and avoiding swampy areas. Its main role? Crucial regional water conservation. It's an incredibly delicate ecosystem. So even a slight shift in temperature or rainfall patterns, those macro impacts we talked about earlier, can throw this vital microenvironment entirely out of balance. It just goes to show how global atmospheric changes directly threaten local water supplies. We see this chain of events most clearly in the ice. Receding glaciers aren't just an isolated event. They're a direct, undeniably visible symptom of global climate change. It is the visual proof of those short solar waves turning into trapped long-wave infrared radiation, melting our ancient ice right down to the bedrock. Which brings us to the end of our breakdown today. We've traced the mechanics all the way from the sun's rays down to the soot-darkening mountain glaciers. So I want to leave you with this. As we continue to weave the threads of this invisible blanket, what symptoms of a changing climate are already visible in your own backyard? Keep observing, keep learning, and thank you so much for joining me on this explainer. Catch you next time.